Hello everyone and welcome to yet another NuclearCraft tutorial. This time we're going to go through the entire Rankine cycle, right from the MSR to the heat exchangers to the turbines, through condenser tubes and then back into the heat exchangers again to generate more steam. It's the full deal. We're going to go through the whole thing, as I said the other day. It might be a long video. I actually don't know how long this will be. I'm literally just going to build a reactor and the heat exchanger and the turbine pretty much just off the cuff. We'll have to see how it goes. If it takes ages, I might cut it down, but let's just see what happens. I just want to demonstrate sort of the thinking process that goes into building one of these setups. I've got a few tools to help me. You might be able to see in the bottom right hand corner I've got the reactor planner, a Hellraiser's reactor planner. I've got a design ready, and I've also got a little calculator here called the Turbine Calculator made by Kirchhoff, or Kirchhoff. That is really good. I think we actually proved, sort of back of the envelope proof, that this will give you the best turbine configuration for a given shaft length. So we'll just have to see. Well, we'll just get into it, and I'll explain when we get to that stage. I haven't got a heat exchanger calculator, which is a shame. I basically just haven't had the time to build one yet, but I have actually got some Mathematica scripts. If you've heard of Wolfram Mathematica, it's a really powerful sort of desktop version of Wolfram Alpha, and I've got these two-stage, one-stage, two-loop, and one-stage files that go through all the maths needed to set up a heat exchanger correctly. Now, when we actually get to that stage, you'll see it's pretty complicated, but as I said, I'll get it onto a sort of spreadsheet, Google Sheets, that you can just type in the numbers you need in, and I'm sure at some point someone who has a lot of time on their hands will be able to build some sort of simulator or planner, a bit like the reactor planner. But for now, we don't have that. And just so you know, I am actually using the normal Hellraiser reactor planner that isn't really built for molten salt reactors. It's more built for the sort of solid fuel reactors. But you can, with the right configuration, sort of set up to sort of simulate an MSR, and I will put the link to the configs I'm using for that equal the MSR cooling rates and so forth, and the fuel, power and heat and so forth in the description. So look for that in the description, and let's just get on with it. So first of all, we've got to build the Monsoor Reactor. Now, as the focus is on the heat exchanger and the turbine and the condenser and so forth, I'm actually just going to use a creative tank to get the fuel from, and I'm just going to get rid of the products. Now, obviously, if you were doing a real setup, you would get the americium, I think I'm using in this case, LeA242 fluoride. That would decay into, well, that would deplete into the depleted fuel, and then you would reprocess that in some crazy setup. But for now, we're not going to do that. I went through that in a previous video on the molten salt reactors, so I'm not going to bother with the sort of details of that part. I'm just going to focus on the steam and how to set that up correctly. So I've got a load of tabs ready in NEI, ready to start doing this. So I'm going to load the MSR pieces, and we're going to just get straight into it. So the first thing I'm going to do, in the way I normally build MSRs, is I normally build the inside, the interior first, and then build around it, build the shell around it. So the design I'm going for here, as you can see, is this one. I'm using LeA242. The base power doesn't really mean anything in MSRs, it's all about the base heat. So in this config setup, I've just got them equal to the same thing. And you can see here that my base heat is 192, and it's a pretty decent build. It's pretty heat neutral, and as you can see, we've got two types of coolants here. We've got glowstone and lapis. Of course, in the molten salt reactor, you use the NaC mixed coolant, so this would be NaC lapis coolant, and this would be NaC glowstone. And here we've got the moderators, which are just moderator housings in the MSR, not graphite blocks. And then we've got 8 cells here, which of course are just vessels. So we just got to build this out pretty much. Now, of course, we have here, instead of actual cells that we just put a sort of controller on and stick a pellet on, we have to actually get the fuel into these vessels. Now, the easiest way to do this would be a distributor, but sometimes you might not want to use a distributor, and I'm going to show you sort of the basic way of setting up a molten salt reactor rather than using the distributors, which are a bit easier. So first of all, I'm going to set up the cells. So the cells, or the vessels, sort of go like that. They sit in the corner. I'm going to put a moderator housing. We've also got a vessel over here, moderator housing vessel, and then vessel, moderator housing vessel. And so that is our structure that we're going to put coolers around. So those are our cells. Now, how exactly do we want to get fuel into these things? Well, I'm thinking that we want to get fuel in from the I think we probably want to do fuel in from the front and back, so that would put into default mode. And we want to do depleted fuel out of the side, so that would be depleted out, depleted out, depleted out, depleted out. And we do exactly the same down here. And out the back, oops, and the front. So now those are set up correctly for the vents. Okay, next what we want to do is we want to put our coolants, our coolers in. So there's a couple ways to do this. Oh, bit of a lag spike there. What we want to do is we want to get some heaters in between here, and we also need to make sure we want to sort of make use of the fact that we can spread coolant around inside the heaters, and I'll show you how to do that now. So let's imagine we have this lattice down here. Let's imagine that we're taking the hot coolant and we're just going to push it through this whole machine and have the we're going to have the normal coolant come through at this side, and we're going to push it through, and the hot coolant will end up on this side, and we'll build all the rest out over there. So let's try and think about how we want to do this. So we want this particular heater to accept fuel, but we also want it to push back the depleted products. So we're going to put this into hot coolant out mode. Okay. Now this heater in the middle here, we want to push into the back side. So that's why I'm holding shift, and so that's modifying the other side of this coolant heater. So that's coolant spreading into there, and then the depleted is coming back. And we also want to spread here. We don't actually want to spread into this one, so this wants to just be a default. And then what we want is I think this one we just want to be a coolant spread as well. So I think that is set up correctly. Okay, now the heater here wants to be on this side a hot coolant out. So we're going to push all of the hot coolant into this central coolant heater and then push it out this way. And then finally we want a coolant heater here, which is going to be a default, so everything's just going to spread to here, and then we're going to have a product out, a heat coolant out. Okay, so that is good. And then finally just this one, which is the final coolant heater, which is going to be a default on this side to accept it, and then we're going to just push coolant into that middle one so it can spread around. Okay, so that is properly configured, and now we can use the hold down shift mechanism, which was actually suggested in the comments. I'm sorry if I can't remember your name. Well, I can't remember your name, but you know who you are. You made a fantastic suggestion to have this ability to hold shift and place the heaters, and they will actually copy their side configurations, which is incredibly useful. And we can just do that 3 times. Or 2 times, and there we go. We've got the interior of our molten salt reactor sorted. Now, of course, the heaters in the middle here aren't actually doing any cooling at all. They're just there as utility heaters to push the coolants into the ones that are actually going to work from this one. So now we want to put our vents on, and we're going to just do it like this. We need to put vents in all the places that we need them, which is all the places where we're either pushing in or pushing out. Here, 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 and here. Now everywhere else can just be wall. Of course you can use the glass as well. I don't think I'm going to use it in this case. So there we are. There's that. Okay, so there we are. That is our molten salt reactor, and if you right click on it, you see we've got 3x3x3, fission vessels 8, coolant heaters 15. Okay, so we are ready to go. At the moment you can see it's a mean heat multiplier of 133.3. I think the reason for that probably is because they haven't got any fuel in at the moment, and so they're reporting incorrect numbers, but we won't worry about that yet. When we put fuel in, it will report the right thing, and in fact we'll do that right now. So let's actually just remember which way around this is. So we've got hot coolant coming out, that's right. So we want this to be where, so we want the back and the front to be where the fuel is coming into. So I've got an actual a thing for this here, so this is going to be fuel. So I'm going to make this super laminar fluid ducts. And I want to make sure that this all hooks together properly, so that's why I've got a crescent hammer here as well, just to make sure that we... this is also the reason I'm not putting any fuel in or coolant in yet, because I don't want things to horribly mix up. That is one of the downsides of using a lot of fluids. Sometimes they can get mixed up, and that can be pretty horrible, but we won't worry too much about that. So that is now all linked up correctly, and if I get myself in this section here, this portable tank, and right-click, all of the... fuel will go in there now, and I think this should be reporting the right values. There we go. So that's a net heat gen of 5632, which is what we have here, 5632, and we have an efficiency of 233.3 and a heat multiplier of 366.7. Okay, so we need to actually wait. We actually need to calculate what we're going to get for the cooling efficiency if we want to do this properly when we get to the heat exchanger, but we'll worry about that in a second. We first of all need to do the actual, the rest of this. So first of all, let's get ourselves more of these laminar fluid ducts. Actually, I might not want to use laminar fluid ducts here. I want to use normal fluid ducts for these ones, and you'll see why in a second. So let's get laminar fluid ducts here. So I can also put normal fluid ducts and then laminar fluid ducts up here so they don't mix. And remember, these top and bottom ones are the lapis, and the middle is the glowstone. Okay, so now I'm going to just push these with servos. Let's get these servos on. Okay, and I want to just bend them. I don't really care about the depleted products. As I say, normally you'd reprocess it, but in this case, I'm just going to get rid of it. So let's do, let's do this. I think that will work. So this is just the bin, universal bin from NuclearCraft, just delete stuff. So all of the depleted products will just go into those bins and get killed. Okay, so that's now good. I'm probably going to put a lever down here as well. Why not? Okay, so that's good. So we've got all of the fuel sorted. So now we need to worry about these coolants. Now, I'm actually only going to worry, for the purpose of the tutorial, about the lapis coolant. Obviously, if you going to set up a normal one, you'd have to worry about all the coolants. In this case, I'm going to worry about the lapis only, because all you basically have to do is, if you're dealing with different types of coolants, is you just have to set up 2 different heat exchangers for the different types of coolant to generate the first lot of high pressure steam. But I'm just going to forget about the lapis for now, about the glowstone for now. Well, maybe not actually. Let's just see if I can be bothered. But for now, let's get this laminar fluid duct out here. So this is where it's coming in. So we want to make sure that these have the same source. So this is going to come out here, and let's just make the source for the lapis coolant come out there, and let's have the source for the glowstone coolant come there. So these will just be the sources, and this will go through the reactor and come out the other side. So this is where a hot glowstone and hot lapis will come out from. Okay, so what we want to do here is now think about building the heat exchanger. So this is the first stage, and for this is where we have to dive into this Wolfram Mathematica script. Now I'm so sorry, this is going to be a bit weird and complicated, but unfortunately I haven't built a simulator or a proper spreadsheet for this yet, so you'll just have to deal with how I've had to in the past work out how to balance stuff. This is usually how I do like balancing stuff. Okay, so if we go into, I want to make a 2-stage system. I want to do the full-blown 2-stage system. So I'm going to go into here, and you can see there's a lot of maths. Okay, I'll explain what this all means. So first of all, what we want to work out is how many contacts we want to make between the heat exchanger tubes that are carrying the hot coolant and the heat exchanger tubes carrying the first lot of water. Okay, so what we want to do here is we want to take into account the fact that in the end, if we look at this recipe here, so let's think about what we actually want to do. In these heat exchanger tubes, we're going to have hot coolant turn into normal coolant, and we're also in the process going to heat up water into high pressure steam. Now high pressure steam is then used in the turbine to become exhaust steam. Exhaust steam is then sent back into the heat exchanger to turn to low pressure steam, right? And low pressure steam goes back through the turbine to turn to low quality steam. Okay, the low quality steam is then sent through the condensation tubes, which we'll get to when we get to this stage, into condensate water. The condensate water is then heated in the heat exchanger tube into preheated water. Now this is a much more efficient way of generating more high pressure steam. So we want to take into account the fact that in the end our cycle is going to use preheated water and not water. In that case we need to use a cooling provided of 800 and a heating required of 16,000. And as you can see in this system here, I've already got that. So I've got water-based cooling provided, 800, water-based heating required, 16,000. So that's already there. The rest of these numbers we'll get to when it matters. These numbers you really don't have to worry about too much. They are literally just to do with the calculation. You can technically, if you're really into this sort of stuff, which almost no one will be, you can do this all yourself and try and work it out, but it's already here. If you have Mathematica, which not many people do, ask me for these scripts and I will send them to you, or I'll put them in the description if you want them, because these might be very useful for you. Okay, so what we have here is just a load of calculations that I can just activate. So there is just set all those constants. Oh, actually, we need to be careful about these constants. So we're going to deal with lattice for now. So the lattice base cooling rate is 480 in the molten salt reactor. This coolant heat multiplier, it just tells us about how effective the coolant is in the heat exchanger. This is just a config option, and you actually just multiply 125 by 480, and that gets you 60,000. And that 60,000, you can see here, is actually just this number here. The cooling required is 60,000, so that's what that 125 is there. You just multiply this config option by the cooling rate in the MSR, and that gets you the heat required to cool it down. Our MSR cooling efficiency, well, to work this out, what we need to do here is we take the ratio between the heat gen and the cooling. This is the definition of the cooling efficiency. Ratio between the heat gen and the cooling, which is 5632 divided by 5920, and that is 0.95135 blah blah blah. But then we also want to multiply this by the efficiency of the reactor, which is 233. So that 233.333, just to get it really nice and accurate. It's actually 2.33 if we're going to do it properly. And that is our cooling efficiency. So let's get that ready to go and put it in here. So there's our cooling efficiency. Number of heaters, well, the number of heaters holding lapis is 8, so that's fine. Coolant tube conductivity. So what is the conductivity of the tube that's going to carry the coolant? Well, in this case, what I'm going to use copper heat exchangers for coolant and hard carbon for everything else, just to mix things up. So in this case, copper has a heat conductivity of just 1, and hard carbon has a conductivity of 1.1. So in this calculator, I want to have a water tube conductivity of 1.1. Water tube conductivity, exhaust steam tube conductivity is also going to be 1.1. Condenser conductivity, as you can see, this is also going to be 1.1. And the condenser conductivity, I've got this condenser tube here, which is actually a thermoconducting alloy one, which is 1.25. So we're going to put 1.25 up here. Okay, and the surrounding temperature, we'll get to what that means in a second. I'm actually going to set this to, I think, 4, and you'll see why later on, but we'll worry about that later. Let's generate all of those constants. Boom, that's ready to go. Coolant per recipe, that's self-explanatory. We've gone through all the rest of this stuff, and now we also need to just run this script to generate all the numbers we're going to need to do our setup. Boom. And by the way, as you can see, it actually calculates the amount of power we're going to generate in the end. The amount of power that this generates is 41,859.5 RF per tick, which is pretty good for that small reactor. The sort of equivalent you might be able to see in here, as you can see, the actual equivalent here is, in RF per tick, is like 3,000. So this is going to generate like 10 times the amount that a normal solid fuel fission reactor would normally generate of this type. Of course, there's more work you have to put in, but 10 times the amount of power might be worth it if you are dedicated. Okay, so now we have everything we need. So all the numbers we need are in here. So the first number we need is the number of coolant water contacts. Okay, this tells us how many sides need to touch between the water heat exchanger tubes and the coolant heat exchanger tubes. So this number here is 47.5. So let's build 48. Let's build like 50-ish. That means that we're going to have enough. We want to build at least that many, because if we build less than that, then we won't have enough to do the process. And in fact, the hot coolant will not be able to get through the heat exchanger fast enough. So let's build our first heat exchanger here. So I want to build it a little while away, because the last time I did this in a test world, I built everything way too close together, and it was absolutely crazy. So I'm going to build it 1, 2, 3, 4, 5, 6, 7, and I'm going to build it here. Okay, so we want 50 contacts. So let's think about how we want to do this. Let's build it roughly the same sort of area. Okay, so the coolant is going to come from the lapis. Now what we want to do probably is, how do we want to do this most effectively? For now, I think I'm just going to do something like this, something really simple. And of course we want to do this as well. Okay, I think this will work nicely. I think this will get us a lot. So that means that we have how many contacts we have. Let's put them down here as well. Yeah, I didn't even think about that. Okay, so here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 contacts per face, or 12 contacts per slice. So we only need 4 of these slices, but I'm going to put 5 just in case. So let's remember how we do this. We first of all want to put these all to default. Oh, that's not true actually. let me check this. I actually don't know this. So remember that in real life, if the output temperature of the cooled fluid is lower than the output temperature of the heated fluid, the adjacent tubes must not be parallel. The adjacent heat tube flows must not be parallel. So in real life, in real thermodynamics, if you have two tubes flowing parallel with each other, then the temperatures of the fluids in the two tubes cannot cross. And of course that's very important in some of these cases because, for example, in the case of this NaC alloy, it goes from a temperature of 700 Kelvin to 300 Kelvin, but the water that we're trying to heat up goes from 300 all the way up to 1200. Okay, so the temperatures actually cross, and in that case we need something called contraflow. And what that means is that although our hot coolant tubes can go through this way, we've got to make sure that the water comes back the other way, and that's called contraflow. In the case of NuclearCraft, it just needs to not be parallel, so you can have tubes at 90 degrees, the flow's at 90 degrees, and that will work. That will count as contraflow in NuclearCraft. Okay, so this is the setup that we actually want, and we can do a similar thing back over here. So, well, let's actually build this out. So let's do, first of all, the heat exchange tube. We want a fluid spread on the other side. Input spread, oops. Input spread, and we want 1, 2, 3, 4, 5. Okay, that is where the final one is going to be. And then here, what we want to do is we want to have default. Okay, so we also want to have default here, and then I'm going to build out the rest like this. And this is the end of the line. Here we are. Okay, so this time we want inputs here, input, and we want these to be product out. Okay, cool. And we want these to be input spreads, and now we just want to build these out. So let's first of all do this one. So that will spread this way across the tube. That will spread that way across the tube. That will spread that way, and that will spread there. Okay, we want something pretty similar here. We just want to make sure that we get this all the right way around. I just want to make sure I got that right. Yes, I did. And down here, oops, have I made this difficult for myself? A little bit, but that's fine. We want to make sure that this is a default side. This is default, and this is default, and then we just want to build out the tubes this way. Okay, so that is our heat exchanger ready to go. Boom. Okay, so that is the interior of our heat exchanger. That is correct. So let's build out the frame now, and the bottom. I always forget about this bit. Now, of course, when we actually set this up at the start, this is actually not going to be enough tubes, because at first we're going to have to just use water, because we don't have any condensate water yet. We don't have any preheated water ready to go. So we need to actually generate some first, generate a sort of buffer in the system, in the loop, and then we can get rid of the water, and we can just close off the condensate water in the loop. So for us, at the start, we need to be a bit careful that we don't sort of push the hot coolant too slowly for this to cool down. So we're going to have to just keep an eye on this Monsoor reactor before we generate enough preheated water in the buffers of all the different vents and so forth along the system. But once we get enough preheated water, this will be enough as per those calculations that we just did. Now let's get some transparent ones this time. I like the look of the transparent ones. We need to have vents there, so I'll leave that. Vents there, and at the top, let's have a heat exchanger controller, and then a few more pieces of glass. We just need a little bit of a lever. Let's put it there. And finally, the vents. So the vents just go on the top here, on the side. There we are. Okay, so stage one of this big setup is ready to go. We have this exchanger. Now we just need to make sure that we actually hook this up correctly. So remember, the water is going to be coming out of here. So we want to make sure that we have a good place for the water to go. Now, there's going to be a lot more water than there is coolant. So I'm happy to use, well, what we're doing here, we're using laminar fluid ducts. What I probably want to do is I probably want to just, well, I've got a crescent hammer, so it's fine, but I definitely want to use laminar fluid ducts for the water and the steam, because there's going to be a lot of it. So let's just get rid of that for now. So that is the input. So these are the inputs for the water. So for now, let's just make them all the same. let's just give them a shared source of water. Let's put it up here just to make sure there's absolutely no clashes that happens. And this also needs to be a water as well, so let's be a little bit careful that we get this right. We want to make sure that this has time to escape, or space to escape, so we'll have to do something like this. Bit ugly, but hey-ho. Okay, now this comes over. Let's just get this ready to go. So this needs to come out of here. So that's water. This is the steam coming out now. So the steam you want to sort of collapse together, and we'll probably just do the same thing as we just did there. But this time we don't have to worry about some water source screwing everything up. So let's come out 2 again. Give the steam space to escape, or the coolant space to escape. Round like that. There's our steam. Okay, so now we need to build the line for the coolant, which is going to be a little bit annoying, but we'll just have to deal with that. So let's just build that like that. Okay, so all of those lines are now good to go. So that is now hooked up correctly. That's going into the top, the middle ones, and the bottom. And this can just hook up to here. Okay, cool. I think I might just give that a little bit more space by doing that. Okay, so that is now the line from the MSR into the heat exchanger. So let's put our servos on here to get ready for this. Servo down there, servo down there. Okay, cool. So that is now hooked up, and we also want to make sure, I think this is all ready to go, so this needs to also be ready to pull. Okay, cool. So that is now all hooked up, and we now need to bring the steam round to the next stage. So this is our steam. So this is now going to go into the turbine. So this high pressure steam is now going to generate some energy for us. So water comes in and generates high pressure steam, but we also need the coolant to come out. So that's the final stage that we need to do. And I'm actually probably going to use hardened fluid ducts here just to make things a bit easier, because we don't really need to worry about there being too much fluid to transport, because, well, there just isn't that much to transport, is the reason. So there we go, that's good. We'll bring that across to here. Now we just need to bring this back around the loop. I think this is super laminar, so I can bring it past that. Where does this go? This comes here. Okay, so I see what I've done here. I've made this tricky for myself. But luckily, I can just use something like a tank. So let's just get a tank quickly. Any tank will do. A big tank would be better. Ultimate fluid tank, sure. Okay, so let's get this to here. Boom. Ultimate fluid tank. Get a servo on there. And then bring the normal fluid ducts around. So here they come. And let's just bring that over the top of this high pressure steam tube. Okay, so that is our hot coolant loop finished. So the coolant goes in, gets heated up, goes to the heat exchanger, generates the steam, goes back round again. Okay, so now we have the steam to deal with. So the steam is going to come out of this tube here. And in fact, we don't even need that one. We can just start building out from here. This is going to have to go round. And we're going to have to be a little bit careful again that we don't hook anything up that we don't want. Okay, so now this steam is ready to go into the turbine. So how much steam are we going to have that's going into this turbine? So again, we go to our little calculator that we have set up here, and we need to look at how much HP steam we're going to have. So the HP steam total rate is here. So the HP steam total rate is 1,308 millibuckets per tick. Okay, that's quite a lot. So let's look at how much these turbine blades can deal with. So of course I've never made a video about the turbines before, so consider this part of the sort of turbine spotlight. We're going to build a turbine for the first time. Now the turbine is built a little bit differently to the extreme reactors turbine. There's sort of a few more parts to it, but essentially it's the same idea. You build a big cuboid and you put a shaft in there and you put the rotors on there. But there's a little bit more maths involved, and we'll get to that when we get to Kirchhoff's calculator. So I'm only going to deal with these three blades and stators. There's also a SiC, which is actually silicon-carbon ceramic matrix composite, but you can't actually craft that yet, so I'm not going to bother with this stuff. But this is the best turbine rotor blade. There's better, but there's other ones here. There's two others, which are the extreme alloy and the steel, and there's also a turbine rotor stator. Okay, so each of these turbine rotor blades can deal with up to 100 millibuckets per tick of oncoming fluid, and we know that we have a oncoming amount of fluid of 1308. So we need to have at least 14 rotor blades, so we'll deal with 16. 16 will be good enough. Okay, so now comes to the turbine calculator. So the way that the steam works, the way that the turbine works, is that you put steam into the turbine, and the steam will expand as it reaches the other side of the turbine, just like it does in real life, and then you output the exhaust steam or whatever, or the low quality steam that comes out the other side. Now the expansion rate is different for different steams, so if we have a look here at the recipes, you'll see that the expansion rate for the high pressure steam going to exhaust steam is 1 to 4 or 400%. That means that ideally in your turbine you want there to be a smooth exponential increase in the volume of the steam when it gets from in the time it gets from the beginning to the end. And so you want to make sure that you set up your blades in such a way that have different expansion coefficients. They also have efficiency multipliers, like base efficiency multipliers, just based on how good the rotor blade is. But the expansion coefficient, you've got to try and match to the expansion rate of the steam. Now, sometimes it will be a bit too fast. Now, of course, if you put a load of rotor blades in a row, then the expansion coefficient is going to go crazy. So for example, 1.6 is the expansion coefficient here, 1.6 squared is 2.56, and that times 1.6 again is like some other number that's like 4, times by that again, 6.4, it gets really, really big. And so you've got to counteract the overexpansion by using stators, which basically sort of compress the steam back together again, and that's got an expansion coefficient of 75%. So you want to sort of mix and match your stators and rotor blades such that you get a nice exponential expansion that goes from 100% expansion to 400% expansion. Now that sounds really complicated, I know, and that is why there is a calculator for it. Kirchhoff has built an awesome calculator for it. And as I said earlier, I think we've basically proved that this will always guarantee the ultimate best configuration. So this is basically how it works. Now I know that I need 16 blades, so I'm going to guess that there's going to be one stator in there somewhere. So I'm going to go for a shaft length of 5. I want high pressure steam, and I don't want sick rotors. So I'm just going to go this length only, and it looks like I've guessed it correctly. So it looks like the best combination is steel, extreme, stator, extreme, extreme. Now that gives us 4 stages. So we've got steel, extreme, extreme, extreme. That gives us 4 stages. So that's 4 sets of planes of blades. And if we want to have 16 blades, we then want to just have 4 blades in each of those planes, which means we just want a minimum size turbine with the rotor blades just being 1 in each direction. Okay, so let's actually start building this thing out. So let's go into Turbine 1. Again, let's give ourselves a little bit of space. 1, 2, 3, 4, 5, 6, 7. So let's build this thing out here. Oops. Okay, so it's a 3x3 because we only want 16 blades. So here it comes. So here we want inlets. So we're going to just put our inlet there. I don't think we're going to need more than 1 inlet. Let's just put 3 for good luck. Okay, so now we want our rotor bearing. There's our rotor bearing that's the shaft is going to connect to, and we want our shaft to be 5 long. 1, 2, 3, 4, 5. Now I should say that the turbine rendering, the rendering of the rotors going round, is not finished. So that's the one part of this that isn't finished, but otherwise it does work. Okay, so that is how long we want it to be, and that is our inlets. Okay, so on the other side we need another bearing to end where this rotor shaft is going to, and then we probably want some outlets. So we probably want a few outlets because the steam is going to expand. As I said, 3 inlets here is overkill, but it might not be a good idea. It might be a good idea to have 3 on this side. Okay, so that is sort of that bit done. Let's build the rest of the frame out and the bottom. Okay, so let's just quickly build the inside of this turbine. So, as I said, the blades is the one bit that isn't really finished yet, so it may look a bit weird, but that's how it is. Okay, so let's remember what we want here. We want to start off with steel, and then extreme, then stator, extreme, extreme. So steel, extreme, sorry, steel, extreme, no, stator, is it? Steel, extreme, stator, extreme, extreme. Okay, that looks good. Steel, stator, extreme, extreme. Oh no, that's wrong. Steel, extreme, stator, extreme, extreme. Now I should say that if you don't have the correct blades, if you don't have the same blades in a plane, if you have, like, say a stator there or a steel blade, then the turbine will not form correctly. You've got to make sure that all the blades in the same plane are the same type. So just keep that in mind. Stator, extreme, extreme, and then finally around the other side we have steel, extreme alloy, stator, extreme, extreme. So you can see here in total we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 blades. The stators do not count as blades because they're not blades, they're stators. They don't generate any power, they just stay there, hence the name stator. So that is the inside of our turbine. Let's just build the rest of this now before we get onto the dynamo coils. So let's build this out. So let's put a turbine controller on it. Let's get the rest of this done. Let's actually put some glass here instead of a wall. Oops. So that gives us a nice wall. I'm not going to bother with that end yet. Okay, so that gives us a nice wall, and then I'm going to finish off the top with a bit more wall. There we are, and the rest of the frame. Okay, so now we need to work out what we're going to do with these dynamos. So the way that the turbine works is that the steam goes through and generates power from turning the kinetic energy in the steam, or thermal energy in the steam, into kinetic energy in the rotor blades, into electrical energy by rotating the bearing in a dynamo. And these are the coils that make up the dynamo on the end of the turbine. Now these all have different rules and different efficiencies, and so you can see it's a bit like the coolers, but a bit easier. There's only 6 of them, and the rules are not quite as complicated. So you can see here, for example, must teach at least 1 rotor bearing. So that we need at least 1 of. So the magnesium turbine dynamo coil, let's put there because I think that might be a good idea. And we can also put them on the other side as well. Now the number of dynamo coils you need is equal to the number of bearings. So this would actually be fine. This would be perfectly good for a decent turbine. Of course, we only have 86% here, which isn't that great, but in principle this would be fine. But of course, we can up that efficiency, that overall efficiency, by putting some better conductivity multiplier dynamo cores on here. So that needs to be next to a magnesium. This needs to be next to any other than aluminium. Bit of a wild card, that one. That needs to be next to beryllium, and that one needs to be next to a gold and a magnesium. So maybe that wasn't the best idea. Maybe we want to put that up there instead. I think this would be better. I think if we put this up here, then we put a beryllium either side. The beryllium goes either side, and then we want, so this needs to be next to magnesium and gold. And gold needs to be next to a beryllium. Okay, that looks like it's good. So gold, and then I think we can actually put a beryllium down here, and then that would be a gold and beryllium. Oh, that needs to be next to a magnesium and a gold, sorry. Magnesium and a gold. So how do we get a magnesium again? We get a magnesium from... Oh no, sorry, I just got that wrong. There we go. That's fine. Okay, there we are. And a silver can go down here. So in real life, this is actually the ordering of how conductive these materials are, their electrical conductivity. Silver is the most electrically conductive element, followed by copper, gold, and the others. And that's why we have those 6 materials. Okay, so that is now our dynamo finished, and if we actually look at here, you can see that we have dynamo coils 10 out of 2, so you can see we needed only 2, but that's fine. And you can see here that our expansion is 430%, given by the choice of blades and stators we've made, which is a little bit over, but we didn't really have a choice in that, and I think this will actually tell us that as, well, 4 times 107 is 430, so that's fine. But 430 is the best you're going to get in this case. This planner, as far as we know, is perfect. You can basically prove that it will give you the best result. Okay, so now we can put this steam in. So let's go back to our pipes, and let's get this stuff going. So let's put this in. And by the way, the dynamos is where you extract the power from. I should just say that. Okay, and this is where our steam, our exhaust steam, is going to come out of. Now, for now, I'm just going to dump this. Oops, I'm going to dump this power into a bin because we actually don't need to worry about that for now. This is just setting up the fluid, and we can see how much power we're generating just by looking at the turbine in the GUI. And let's get ourselves another duct there, and that is sorted. So that is our turbine. Now that's going to generate exhaust steam. Let's get a lever on there as well. There we go. Okay, so that is our exhaust steam. So the exhaust steam now needs to go into another stage. Okay, so the exhaust steam. Now, how much exhaust steam do we need to worry about? So this time the exhaust steam, if we look here, exhaust steam, use, exhaust steam, what does that do? So exhaust steam needs to come around and turn to low pressure steam. So here I'm going to have to use some of the hot coolant to heat up the exhaust steam again. So that is taken care of by this, and the amount of exhaust steam coolant contacts that we need to use is equal to 47, so exactly the same number. I don't know why that is, but it just seems to be the case. Okay, so 47. Cool. So basically we just need the exact same build that we had over here, pretty much. So since that's going to be exactly the same, I'll be back when I've built this all again. Okay, so that is the second heat exchanger setup. So what I've done, if you come over here, first of all I actually put servos on here. I forgot to put servos on these tubes, taking the the normal coolant back around again. But as you can see, what I've also done is I have taken some of the hot coolant coming out of the MSR and forked it off down this route. I've swapped over to normal flow ducts for this bit, just to make this piece a bit easier. And it's going through against the contraflow to the steam coming the other way. The reason I remember I need to do that is because the temperatures go past each other, or at least the temperatures don't come together, they sort of go past each other or are already past each other. And so I need to have them in contraflow, or at least not in parallel flow. And then the coolant that's been cooled down by the steam comes back round here and ends up coming back round the other side to the start. Okay, so now we need to take this exhaust steam that has been turned into low pressure steam now. So this is low pressure steam, and now this needs to go into another turbine. So this time we go back into our calculator. Oh, not this one, we go here. So we've done that stage, and now we need to look at the amount of LP steam, low pressure steam. So LP steam, total rate is 5232. Okay, that's quite a lot, so we need a much bigger turbine this time, so that we need at least 53. We need at least 53 blades. So let's go for something like, let's go 53, so maybe let's go for something like 60. So 60 would require maybe, let's say 16, let's go 64. So that's 4 lots of 16. So we can actually use the same design as here. So we could just go for the same design. Let's do that. Oh, actually no, we can't, because it's low pressure steam, so the expansion rate is different. So this will give us a different answer. Okay, so let's see what that does. So we've got steel, stator, extreme, stator, extreme. So you see this time, because the expansion rate is lower, we need more stators to keep the expansion rate from going too high. Let's go to a shaft length of 6. Let's see what happens here. Steel, stator, steel, 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 stator, steel. Okay, let's go for a shaft length of 6. Okay, that should work. And we need a length of 6 on the inside, so that's a total of 8, a size of 8. Okay, we're running out of space here, so I'm going to have to move into this direction. So let's get our turbine pieces and build the next turbine out. So that's going to be 1, 2, 3, 4, 5, 6, 7, boom. Okay, let's build this next one. So this needs to be, oh sorry, this needs to be frame. Okay, so this needs to be on the inside, needs to be 1, 2, 3, 4, 5, 6, 7, 8. Sorry, that's wrong. It needs to just be 6 on the inside. So that gives us a lot of space for wall. How long does it need to be? Well, it needs to be this long, so we need how many on the inside? Wrong thing. We need on the inside 6 length of 6. So that's 1, 2, 3, 4, 5, 6. Like so. Okay, so this is going to be quite a fat turbine. So what I was doing there in my head was to get 64. So we don't need 64, we don't need 53, but I'm just sort of making sure. 64 I got from just looking for 4 lots of 16. So what I actually need on the inside here is not 6. I need 1, 2. Oh, sorry, I do need 6 because we've got 2 lots of stators. But I only want 4 lots of rotors. So 4 lots of 16, which gives us 4 lots of 4. So we need a thickness, a bearing thickness of 2. So that gives us 4 squares of 4 each on each plane. I'll show you what that means in a second when we build this thing out. So this is going to be like a sort of cuboidal turbine. It's going to be a bit weird. And then 1, 2, 3, 4, 5, 6. Okay, so here we want a bearing size of 2 by 2. So this is the difference here. You can actually have different bearing sizes. Any square will work. So I'm going to build a 2 by 2 one here. And we're going to have quite a big rotor shaft going through here. It's going to be a 6 by 2 by 2. There we are. Okay, so let's remember what the order is here. We want steam coming in this side, and I think the order is pretty symmetrical. I think it's steel, state, steel, steel, state, steel. Okay, so let's get our rotors out. Steel. Okay, so remember we need to make sure that, by the way, you can't have a turbine like this. You can't have a turbine where the blades don't go all the way out to the end. You must make sure that you commit to having all the number of blades that goes out to the edge. Otherwise, the turbine will not form. And you can also move through these at the moment. They're transparent, so it's a bit weird, but it makes building them a bit easier. Means that you don't have to worry about getting yourself in a corner. This looks a bit more like a real turbine. The one over there looks a bit like a packet of bacon rashers, which is the unfortunate problem of having extreme alloy. But never mind, you know, it's a bit of fun. The sick alloy or the CMC looks pretty nice actually. It's one of the better textures I've made. I'm not really a great texture artist, but it's one of the better ones. Okay, so there we go. That is the inside of our turbine sorted. Okay, so this time we've got 8 bearings, so we need to make sure we have at least 8. Again, I'm not super worried about power generation, but let's try and think about how we want to do this well. Let's do something like that. Normally stuff like this works for some reason. It just seems to be good with these rules, to just go sort of round. Usually if you have big turbines you need to sort of spread out. You need to start using the aluminium ones, but for the most part you don't need to do that. So here we go. We have magnesium that needs to touch beryllium. So beryllium needs to touch magnesium. Okay, so we can do that. Normally you want to try and keep it all close quarters. Makes things a bit easier. Beryllium. So gold is next on that. Gold. Now I don't think we're actually going to be able to get a beryllium round here, so it may just be better to go for gold and leave it at that. Maybe gold and copper. Let's keep it at gold and copper. So gold, 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 I think, and then copper can just touch a gold. Gold, boom, 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 boom. Oops. So there we go. And then that at the top. Okay, so that sort of fills it all out. And just for completion, let's do that. Just fill it all out. Okay, so that is our dynamo. That is sorted. Okay, and next we have the inlets and outlets. Okay, so on this side, we want our inlets. I'm just going to, I think I might just confine the inlets to down here. Make the rest of these just wall. And I'm going to use the whole of this side for outlets, because we're going to need a lot. And again, I'm going to do that thing of just binning the power, because again, we just don't need it. For this example, we don't really care about this. Of course, in real life you wouldn't do this, or in the real game you wouldn't do this. Okay, so that is our steam turbine. Oh, I don't think I've actually built the haven't built the walls here yet. Let's quickly do that. And there's our controller. And let's get ourselves a lever. Okay, so controller, 40 out of 8, that's good. And the expansion rate is 216, which is 108 times 2, which I'm sure it says here. Yep, 108 times 2. Okay, so that again is as good as we're going to get for this turbine. So see there that this is an example of how, even though the steel turbine rotor blade is actually the worst out of these two, here it was just fully steel, just because of the way that the expansion rates ended up, and here we use mostly extreme alloy. So it's not a guarantee that you just want to use the best rotor blade. It's to do with these expansion levels and making sure that you've got as smooth of a exponential expansion across the turbine as possible. Now, when you are using the SIC blades, usually you hardly ever use steel. When you use the calculator, you'll find that the steel hardly turns up, but that type of material is going to be very, very difficult to make, and of course at the moment is not even craftable at all. So you have the choice of these two for now, and so steel does turn up quite a lot. Okay, so let's get this steam around to here. So this is all good, all dandy, and let us bring this around to here. Let's get this all hooked up. So I hope that these laminar fluid ducts are going to be able to deal with this ridiculous amount of steam that's going to be piped out, because the amount of steam is actually expanding as we go through each of these turbines. So by this stage, there's going to be a huge amount of fluid flowing through. I haven't actually put servos on here. I probably should, yes. servos go on vents and inlets and outlets. Vents and outlets will not automatically push fluid. Well, maybe outlets do. I actually don't know. But vents certainly don't. That would lead to all sorts of problems if they did. Okay, so that is the inlet sorted, going through the turbine, and now we end up with the low quality steam. This is the worst of the steam. This is the final product that before this latest update had no use. So low quality steam now needs to be condensed. This is the only thing you can do with it. It needs to go through a condenser or a set of condensation tubes to be turned into condensate water. Okay, so remember here that we have the best condensation tube. We're going to use the thermoconducting alloy, and we have that set up in here, I believe, yes. And so the number of condensate water contacts, now remember up here I set the liquid steam condenser surrounding temperature to 4. Now this is the temperature of liquid helium. I'm going to fill the condenser with liquid helium to cool down this low quality steam, turn it back into condensate water. Okay, so we need 9. That's how good liquid helium is. As you can see here, the actual equation involves the logarithm. So the logarithm between the difference of the fluid that is going in. So the low quality steam has a temperature of 350. The surrounding temperature is going to be liquid helium, which is 4. You take the natural logarithm and you add that to 1, and that is your multiplier. And that multiplies the base conductivity of the tube, and that gives you the total multiplier for the speed of the condensation. The time that it takes is given there. Heat removal required is 40. And it's just 1, the sort of rate that you get is just 1 for every touching liquid, and then multiplied by those multipliers. So for example, in the case of liquid helium, if we just do a quick calculation here, so liquid helium log 1 plus log 350 over surrounding temperature, this comes to, I think, oh I don't know, I need to put n around this, that's how Mathematica works, to get an actual number. So 5.47, so that's the multiplier for liquid helium. If we were to use water, that would be 300, and so the multiplier is much lower, so we need about 5 times as many water coolant contacts. But here we only need 5 because we're using liquid helium. And then we also get multiplied by the steam condenser conductivity, which multiplies it by another 1.25, which gives us that nearly 7, so nearly 7 times the speed in the tubes. So that's why we only need 9, which is pretty good. Otherwise, we'd need, what would that be? About 60. Okay, so let's build this thing. So this is just a heat exchanger, but it's a bit different because we actually put fluid into the heat exchanger. Okay, so let us build this out. 1, 2, 3, 4, 5, 6, 7. So we only need 9 this time. So we could do 3 lots of 3. That would work. I don't think we can build that though. We could do 10 and then do 2 lots of 10. Let's do 2 lots of 5 then. So 2 lots of 5 contacts. So that would be here. 1, 2, 3, 4, 5, 6, 7. Boom. So 2 lots of 5 contacts. So that would mean that we have a condensation tube here and here. So that would literally be the whole thing. It would just be up above and below. So that is literally it. And how many lots we have? We have 5 lots. So that would be from here. And that is, sorry. 1, 2, 3, 4, 5. So that is the end. So it's just a mini condenser, but that does the job, so we don't have to worry about it. And there's one more up here. Oh no, there isn't. Sorry, that's it. That is it. There we are. So these condensation tubes are going to be after working overtime. It's not too many of them, but we don't need many of them. That's the great thing about them. They are pretty fast if you have a cold fluid around it. Okay, so let's get some nice glass to hold the liquid helium in. It's going to be pretty cold in here. Let's get some vents. So we want to make sure it's exactly the same rules as before, they're just different types of tube. So default side there, get over the top, fluid spread, and then 2, 3, 4, 5, 6, 7, 8, 9, 10. Output on this side. Sorted. Okay, let's put some more glass here. I'm going to use glass this time because I want to have a look at that liquid helium in there. And I'm going to put the exchanger controller on the top here with a lever. Boom. Okay. Build the rest of this out. Okay, I've just realised that I'm going to need to get into this place. We're going to have a bit of a helium spillage, but I'll just prepare for that by doing this. And I'm also going to need to get to the top now that I think about it. Okay, so now let's get this liquid helium in there. There's no glass there. That would be a mistake. Vents. Okay, liquid helium. Here we come. So now, liquid helium is used for something other than coolers. It's now used as condensation cooler as well. And this stuff will not disappear, will not evaporate or anything like that. It will just sit there. Okay, so let's get this all in there nicely. Sitting there, liquid helium. Cool. Okay, this stuff flows pretty fast. It's super fluid. Okay, there we are. And we can just seal this off. And we have dealt with the problem. Cool. And we need to get another lever. And get our heat exchanger controller. And there is our condenser, our liquid helium condenser. Pretty cool. Okay, so now let's get these pipes going all the way around here. So let's pull out of these vents. Okay, so let's bring all of this together. Like this. And bring it down like so. Okay, there we are. So all of that low quality steam, loads of it, will get condensed down into a tiny amount, well not a tiny amount, but a lot less condensation water, or condensate water. And that gets pulled out of here. Okay, so there's our water. Okay, now what do we need to do with the water? The condensate water. So let's look at this. Use of this is to make condensate water. And the use of this now needs to go back into a heat exchanger, and the condensate water needs to be turned into preheated water. And again, we go to our calculator. How many of these condensate water contacts do we need? 9. Oh, sorry, that's the wrong thing of maths, isn't it? It's number of condensate water cooler contacts. Oh, I may have made a mistake there. I used the wrong thing, didn't I? How many is this? Number of low quality steam condenser contacts. We need 30. 30 there. Oh dear. Okay, well I've made a mistake there, haven't I? Okay, I'm going to have to go back and fix that. I'll do that quickly. But as you can see, we only need 9 water coolant contacts in our heat exchanger. Sorry, I took the wrong value down. That was the problem. You may have noticed that when I did that. But don't worry, I need 30. Okay, I'll build that quickly, and then we'll get started on this next heat exchanger. Okay, so that actually wasn't too bad. I just extended it outwards by 2. Turns out I actually ballsed up the maths anyway, so it wasn't actually that much of an expansion. So we needed 30, remember, and up here we have a total of 1, 2, 3, 4, 5 times 4. That's 20 contacts up there and 20 more down there, so 30, that's plenty. Okay, so that is that condenser sorted. Okay, so now we need to go back to this condensate water, and remember we needed 9 contacts with the hot coolant. So I've got to bring I need to bring more hot coolant round. So on this huge loop that's being done. Now this time, I don't think we actually need to do contraflow. If we actually look at the heat exchanger map, if we just look at this here, the contraflow rule is only if they go past each other. Now this goes from 700 to 300, and the condensate water goes from 300 to 400, so it does go past each other. So we do still need contraflow. Okay, never mind me. Okay, so let's bring this around. So this is our coolant. Let's bring this all the way around. This is going on a big journey. Sort of tempted to use like an ender tank or something at this stage. Okay, so let's get that ready to use. Okay, so now we just need 9 contacts. So we can do the same things we did over there, but we can just make it 1 thick, or we can just do something a little bit simpler, which would just be sort of 1 in the middle surrounded by 4, and we can do that 3 times. So that would just mean a little bit less annoying cabling. So let's build that out. 1, 2, 3, 4, 5, 6, 7. And I don't think, so this needs to be exactly the same, so hang on, this needs to be 1, 2, 3, yeah, this needs to be 1 less. And so if we're going to have 3 across, so yes, 3, 1, 2, 3. So it's going to be a cuboidal heat exchanger. Okay, so here we go, here's our next exchanger. As you can see, I've left out the ones in the corner here, so that means we've only got 4 contacts per row, per frame, per plane, which means you have 4 8, 12, which is more than 9, so that's fine. Okay, so let us get some more wires, or not wires, but more cable. There we are, and let's just hook this all together as usual. Okay, that was much easier that time. Okay, so that's all hooked up, and that's the preheated water ready to go. Probably want to hook it up like that. Okay, cool. And this needs to then come out and then go all the way back round. Okay, so let me just build this out and I'll be right back. Okay, so there we go. That line that's coming back is now hooked to this line that's coming back, and that will get fed back into the MSR. So there we go. Remember, this is a tiny MSR. We're not even dealing with the glowstone here. Remember, we're only dealing with the 8 lapis coolant heaters. So when I said before, you know, don't build too big with this stuff, I think I said that in the original MSR video. This is why there's a lot of work that goes into it. Only build small MSRs, okay? That is almost like a guaranteed thing you should definitely do, is only build small MSRs. Okay, so as I said, yeah, we're definitely going to forget about this this glowstone. We're not going to bother with it at all. So I'm actually going to just spin this over to the side and just bin it, because otherwise that would just be way too much work. Okay, so there we go. We have the preheated water, or at least we have the preheated water stage ready to go. This is our preheated water output. The preheated water is now what goes back into the original heat exchanger. So the water is coming in from, I think, here. Here is where the water comes in originally. So the water comes in here and goes through the whole system. But we want to bring, this is where we want to bring the water back to. This is where we want our preheated water to come into. So now we bring this all the way over everything. Bring this all the way back round, the whole system. And this is where the real stuff starts. So I'm now going to go back on what I just said, and I'm going to do that. I'm going to bring this round and past all these other cables. Underneath there. Probably above actually, because we're going to have to go higher. Let's go all the way back, past this stuff, past the condenser, past this turbine setup, the low quality, sorry, the low pressure turbine. Let's bring that above. Okay, so we are back here to where we need to be. Okay, so this is where the line ends. Okay, now what I'm going to do is I'm going to start building up a big buffer of this stuff, and I'm going to put a big tank here. So let's get one of those tanks again. Big mechanism tank. I'm going to get a load of them, I think. Well, not a load of them, but at least a good number of them. So let's get one here, one here, one here. Okay, so that should give us enough of a buffer, I think. Let's put one more for good measure. That should give us enough of a buffer for the whole system. Boom, boom, and boom. Okay, so that is all of it. That is the whole thing. Okay, so now we just need to start generating some actual steam to get this system going. So everything is in place now. Everything is in place, ready to go. This is the moment of truth. So let's just go through everything again. The MSR is here. We're putting fuel into it. We're not worrying about the depleted products. Normally you reprocess it. That heats up the incoming glowstone and lapis NaC coolants. Heats them up. We're going to forget about the glowstone for now. The lapis, the hot lapis coolant, comes into the first heat exchanger and exchanges its heat with water to generate high pressure steam. The high pressure steam goes into a steam turbine to generate power and exhaust steam. The exhaust steam goes through another heat exchanger and heated up by more hot NaC coolant to turn into low pressure steam. The low pressure steam then goes into a bigger turbine to generate low quality steam and power. The low quality steam is condensed into condensate water, which is then heated with more of the hot NaC to generate the preheated water, and the preheated water goes back round to complete the cycle. And we should generate, as we set up here in the top, should generate around, let's look at the power again, about 40,000 RF per tick. It will probably be a bit less, or it might be a bit more. We'll have to just see how it goes. So here we go. This is the moment of truth. So let's. I'm actually going to make a backup of the world in case something goes wrong, because I do not want to build this whole thing again. If I've made a mistake, I'll find out and then come back. So let me just back up the world quickly. Okay, we're ready to go. So let's just turn on everything that we need. Turn on this, Turn on this, turn on everything in the line before we turn on the MSR. So everything is activated, turbines are activated, condenser is activated, heat exchangers are all activated. Okay, so let's go back here. And remember, we first need to actually get some of this coolant going. So this glowstone coolant, I'm just going to make a creative, I'm going to make it a creative portable tank of glowstone. So portable tank, here we go. Boom. And I'm going to make this a creative glowstone. Glowstone NAC. There it is. And that will fill the glowstone coolants up. That will go in there, and hopefully we'll start to do some cooling if it goes in. Ah, that is hot. That is hot eutectic NAC. I didn't want that. I wanted the cold stuff. Okay, that was a mistake. Let's get rid of that vent and all of this stuff. And try that again. Oh dear. This is a blunder. Okay, get rid of that. Let's try that again. Portable tank into output mode. Creative thing. Boom. Okay, this time normal eutectic NAC. This should work. Okay, now that goes into the heat exchanger, and there we go. Okay, now that's doing some cooling. So that's doing like about like a third of the cooling, and now I need the lapis to do the other 2/3. And so for the start, I'm just going to put again another creative tank up here just to get the buffer going of this stuff. Creative, and this time we want the lapis. So yes, as always, you do need a bit of a buffer to get going. There's the eutectic NAC. Lapis. So that's now filled up all the pipes involved. And now we go. Net heat gen 288. So we turn this thing on. We have to be a bit careful. In fact, what I might do, we can actually do something else here. We can actually put a sort of little safety loop here. So let's do that. So let's get ourselves some redstone ports just to make sure that nothing goes wrong. So redstone port, there it is. So where should we put these? We can put these. Have we got like red alloy wire and stuff? We do not. So we're going to have to do something down. Well, it's going to be down here, I guess. We have to do it underneath the ground. Well, no, we'll see. So that goes there, and we'll just have to do one like, I don't know. Where should we go? I guess it's going to have to be up here. Okay, so that's a little bit weird, but that's all we have. Okay, so this is going to be our comparator. So this is just a little example of how to use comparators. So here is our comparator. I think actually we don't need a comparator. Oh, yes, we do. We do need a comparator. Comparator. Redstone comparator. Goes here. This will output a signal proportional to the heat. Let's get a redstone torch and some redstone dust. Okay, that looks pretty shocking, but that's what we have going for us. Okay, the reactor is on. But we don't need that anymore. Okay, so the reactor is actually running, and it's generating hot eutectic NAC coolant. That is going through here. That looks to be generating. Is it generating steam? Oh, we haven't put any water. We haven't got any water going. Oh no. Okay, hang on. Water. Let's get an infinite water source quickly to get this whole thing going. So we need to start getting the buffer flowing. Oh, wrong thing. Okay, water, go in. Okay, now I think we should be generating steam. Are we generating steam? What's happening? Okay, so we've made a mistake in here. Looks like I forgot to do something. It looks like the lapis is coming through properly. It just doesn't look like the steam is. So let's have a look in here. Have I made a mistake? Yes, there you go. I did make a mistake. Okay, so simple little fix. Let's just make sure we do this systematically. And tube. So luckily that wasn't too big a problem. And we have it sorted already. Boom, boom, boom. Turn that back on. Okay, it's ready to go again. And it looks like there is steam. I can see the steam now. There it is. Okay, cool. We can turn this reactor back on. And we can get back to see what's happening. Okay, so steam is going into the turbine. It is being used up at a good rate. Okay, the turbine is generating about 8,000 RF per tick. The input rate is pretty slow, but it's building up. Okay, this is our low quality steam, sorry, our exhaust steam. Our exhaust steam is going into here, and our exhaust steam is, looks like it's active, looks like things are happening. Is there coolant coming out of here? Because I can't tell because of the massive amount of stuff going on. Exhaust steam looks like it's stuck. It looks like it's stuck. Oh, maybe not. Is it stuck? No, that looks like there's steam in there. Okay, steam is going into the turbine. The turbine here. It looks like it's getting steam. There it is. Steam is going into the condenser. The condenser is generating the condensate fluid. Okay, the condensate fluid is coming here. Is that generating anything? Hard to tell. Let's go inside and check. I may need to go into the center or something to check. Is it worth doing? It might be worth doing. It's got nothing. That's got nothing, so there is something wrong there. Ooh, bit of a lag spike. So this heat exchanger, remember, let's turn this reactor off again. I just want to make sure that it's all working before we let this thing fly. So this thing, it looks like I made a mistake. So the condenser fluid's coming in there. It just doesn't want to. Maybe there isn't actually any fluid there, and it's like ghost fluid. Let's put a tank down here. Yeah, I think it's just ghost fluid. I don't think there is actually anything there. I think all the buffers need to fill up. This thermal expansion stuff is really confusing me. Okay, so this is still fine because it has an unlimited supply of coolant, so we can actually leave that on. But we just need to wait for everything otherwise to sort of get up to speed, if you will. So this thing is still not really up to speed. This thing's still sort of waiting on stuff to come round. I think there's still not all the tubes in here are active. Well, all the tubes here look to be active now. All tubes active at 88.9%. That's pretty good. I think probably the reason that this isn't up to speed, now that I think about it, is probably because we're not using preheated water yet. This is still the water stage, so there's not going to be enough steam coming through. Or there's not going to be as much steam coming through. That's probably why it's running slow. That makes sense now. So we just literally need to wait for these buffers to start building up, which just aren't yet. So we just need to wait for there to be enough hot coolant in the system, or that the hot coolant starts going into this heat exchanger over here. So I'm just going to let this system sit for that to happen, and I'll be back when it does. And so, with a little bit of help from a little creative tank of hot knack later, just to speed things up a bit so I don't have to wait so long, we finally have some preheated water coming through and filling up these buffers. And here we are. It's doing pretty well. I'm going to wait for all these 4 buffers to fill up before I hook up the preheated water. It's getting pretty exciting. I'm looking forward to seeing this whole setup in full action. As you can see, these turbines are not able to quite. Oh, actually, no. The input rate here is pretty good now. Look at that. It's always all the way up to 100 millibuckets per tick. That really is surprising. This is all chock-a-block. Is this chock-a-block? No. It might just be. Maybe there's something wrong with the fact that. Oh, maybe what's happened is that this has slowed down. Aha. Maybe this is what's happened. So this has slowed down because this can't cope. Aha. And now that means that this can't cope. Yes, that's what's happened. Okay, so the problem is that the laminar fluid ducts are not able to cope with the amount of fluid that we're pushing. That's quite annoying, actually, because laminar fluid ducts are meant to be really good. So the choice is to either build everything a bit bigger or to use different pipes. I'm leaning towards using different pipes. Okay, let's use some different pipes. Let's use Mechanism's Ultimate. There's also a more called pressure pipes, but I don't have that installed, unfortunately, so I'm going to have to go with Mechanism's tubes. Mechanism mechanical tube. Now, this is going to be a little bit annoying because we've already got fluid in all the pipes, so hopefully this is not a massive pain. If we turn all this off, hopefully it won't be too bad. If we bleed the system, if we bleed the pipes of all the fluid by using bins, then we might not have so much of a problem. Okay, so this is the first one that's wrong, isn't it? So let's just bleed this first by getting a universal bin. Okay, so let's get rid of all that. It might just be a good idea to go like this. There we go. Okay, cool. So that's all gotten rid of. Let's get all of these pipes sorted. Okay, so I've nearly done all of this mechanism cabling. If you take anything from this video, make sure that you take into account just how much steam is going through these pipes when everything starts expanding. It looks like thermal expansion pipes start to really struggle with the amount of fluid you're trying to push around. So I recommend mechanism pipes because they're pretty fast, but they're a little bit laggy. Pressure pipes is the other option. They can push a ridiculous amount of fluid. A pretty simple mod that you can get off CurseForge. Highly recommend that. So it looks like now we could be in business if we just turn everything back on. Let's get everything going. There's turbines and the exchanger's back on. Did we turn this off? Yes, we did. That's good. That's good. And this exchanger on. And finally, this back on. Okay, so that is back on. This buffer is starting to build up nicely, and it looks like it's starting to get through all this. Okay, you look at, there we go. Yeah, it's starting to get through all the steam now. Okay, so what we said previously when we said that there wasn't enough steam going through, that was true. It was just that it wasn't being pushed fast enough. That was the problem. So now it looks like all this is starting to back up. We're going to wait until it really has fully backed up. So this is nearly completely full now. 170, 119, 120. I'm going to wait until these vents start backing up before completing the loop. Once these vents are full, that means that the entire system is saturated with water, and I can put the preheated water through, and we don't have to add any more water to the system. So we're pretty close to that point now, which is pretty exciting, really. It means that we'll finally have our system in full swing, which is pretty nice. We can actually have a quick look in here to see how close we are to that. Okay, a little bit more to go, but not much. Okay. This is pretty good. This is the first time I've actually ever built the full two-stage cycle. I've built a few one-stage cycles with steam loop. So the other option you have, this is the most efficient setup, by the way. The two-stage cycle, when you have the high-pressure steam going in and then the low-pressure steam going in, that is the most efficient. There's two other ways to do it that don't include using other mods turbines. First of all, you could, instead of generating high-pressure steam and putting that into a turbine, you can use the high-pressure steam to generate steam by looping it back into a heat exchanger and then putting it into a turbine, and that will generate you a little bit less power, but it's still pretty good. And the sort of least efficient way is to just generate the high-pressure steam and then dump the exhaust steam. And of course, that's a possible option. That would mean that after this stage, you would just dump everything. Or the other option is to put the exhaust steam straight into this condenser, so you can just skip the low pressure stage altogether if you want to. So there are lots of different ways to do it. It's up to you, but this full setup obviously is the most efficient because you get two turbines and also this preheated steam loop is sorted. Okay, I'm going to say that this is pretty much ready to go, and I'm going to complete the buffer by looping this up. I'm going to just drain this entire system of water, drain these pipes of water, these laminar fluid ducts. Let's get rid of all the water in them. Okay, cool, that looks all good. And these buffers are nice and full. Those fluid ducts are gone, so we can finally complete the cycle like so. And there we are. That is our full Rankine cycle complete. The preheated water, once all this water has run out, will go into the heat exchanger and go back and convert itself into the steam and back into preheated water. Okay, so that, I think, is pretty much good to go. I think also this buffer, we don't need this anymore. So that is now a self-consistent, self-complete cycle. Obviously this glowstone we didn't worry about, but the lapis is fully self-complete now. The lapis gets turned into hot NaC, which gets used in various places along the cycle, and now we are generating the maximum amount of power that we can. So you can see here the input rate is like 29%, 45%. What I'm going to do actually is I'm actually going to get rid of these vents and replace them. In fact, another thing we could do is we could just, one of the things that was added recently was just clear all fluid. Let's just clear everything in there and just get everything going again. So what is not keeping up? Is it the hot coolant? I think because I cleared out, when I cleared out that exchange, I lost a huge amount of hot coolant. Hang on, let me fix that problem just briefly by doing this. Boom. Just fill that buffer up again. And get everything sorted. There we go, that's good. Okay, so this thing is generating like 20,000 RF per tick. This thing is generating about 20,000 RF per tick. So there we go, that's the 40,000 that we predicted from our maths. There it is, so fantastic. So that is the complete Rankine cycle. That's pretty cool. So there we go, so that is the full thing. As I said before, you can cut off at any stage. It is pretty involved, it is pretty complicated, but that's what I wanted NuclearCraft to be about. I wanted it to be about big, complicated systems, and this is pretty good. This is what I wanted right from the start, and I really hope that you enjoy this. Everything is working out. There's been a lot of bugs, involved with these multi-blocks, ever since October, but all of them, as far as I know now, are ironed out. The condensers are in. The full Rankine cycle is complete. So yeah, that is pretty cool. It's pretty cool to see happening. So thank you all very, very much for watching. And if you have any questions, of course, please do ask them in the comments. This video is going to be incredibly long. I'm sorry about that, but that's just the way it is. I wanted to just do the full thing, demonstrate how to build this whole thing. Maybe I'll put some timestamps or something. I won't be able to do it tonight because it's now 4:15. I need to wake up pretty early in the morning as well. It's going to be a bit of a difficult morning tomorrow, but never mind. So yes, I will end it here, and once I come back from uni, we'll get started with sided configurations for machine side configs, which really needs to be in the mod. That's the final sort of tweak that needs to be done to this mod before we move on to the overhaul, where we redo the solid fuel fission reactors and the fusion reactors, which, I personally believe, the fusion reactor is probably the easiest of all. They generate loads of power. They're pretty overpowered, really. But to be honest, I'd rather have this system set up than that one over there or that one. This is what I want NuclearCraft to be about, these huge complex systems. So yes, thank you very much for watching, and I will see you next time. Goodbye.